Hi. So here we go. Math 204. And in this particular video, I want to go from section 3.4 all the way through to section 3.11. Don't worry, most of them are pretty short. Okay. So, theorem. Well, let me say that we know that a function, complex numbers, to the complex numbers, differentiable, f equal to u plus iv, has something to do with the Cauchy-Riemann equations. The partial derivative of u with respect to x is the partial derivative of v with respect to y, and the partial derivative of u with respect to y is equal to minus the partial derivative of v with respect to x. There is another way to say this. Well, there's something that's related to this theorem. If u and v from the real plane into the real numbers have continuous first order partial differentials, that satisfy the Cauchy-Riemann equations, then second derivative of x, u, plus second derivative of u, y, is equal to 0, and the same is true for v. Proof, it's exercise. It's pretty easy. Just take derivatives, manipulate them, partial order-y things, add stuff together. It all works. Also, it's given in the notes if you want a worked example. So this thing here is going to be, I'm going to define it as the thing that takes second derivatives and with respect to x and y, and it is called the Laplacian. Laplacian. It's an example of a differential operator. It takes a function and it spits out another function by taking derivatives. So that's very important. And this thing up here can be stated as saying that u and v. The Laplacian is phenomenally important. So I should say, for an arbitrary function, this is the second derivative of f plus second derivative with respect to y, f. The Laplacian is phenomenally important. Black and Scholes are two people who worked out how to price European options. So an option is a financial derivative that allows people to effectively make a bet about what the price of, say, some underlying good might be, like the price of oil, or the price of wheat, or the price of stocks in some company. So you make a bet in the future about it, and then you sell that bet to somebody, or you buy a bet from somebody else. It turns out that the prices of such bets is governed by solutions to the Laplacian. In particular, something called the heat equation, which is related to the Laplacian. And the heat equation describes how diffusion occurs. So it describes how heat transfers through a metal rod if you're heating one end, for example. And because the solutions of the heat equation are related to solutions of the Laplace equation, and because solutions of the Laplace equation are related to complex analytic functions give you a very neat and convenient way to describe how heat flows through a solid. Now, if you have a weird shape for a solid and you'd like to work out the answer, maybe you can perform a complex transformation of the plane to make it easy to work out what the complex analytic function would be that solves the various equations. And then when you undo that complex analytic function to get the u and the v, you get some equations which physicists, for example, might call the equations that describe the potential and the force. So solutions are also related to fluid flow because of this connection to diffusion, electromagnetism, because the Laplacian gives you the Poisson equation. The Laplacian is related to Brownian motion, which is one of the things that made Einstein very famous. And so it's also related to stochastic differential equations and path integrals in quantum mechanics. So what I want you to take away is the Laplacian is a very, very important, very, very cool thing. And the fact that complex analytic functions that are complex, that have derivatives, their real and imaginary parts must necessarily satisfy the Laplace equation. Well, that's pretty cool. Now, I've spoken a lot about metaphors for mathematics in terms of food. Well, this is meat. It's a three-course meal. It's maybe even more than that. It's a large steak, several of them, if you like steaks, or if you don't, then it's some equally amazing type of other food that you really enjoy and will fill you up for a long time. I like baked potatoes, so this is a sack of baked potatoes with whatever you'd like to put on them. Anyway, it's cool. And the more time you spend in mathematics, you'll more see that the Laplace equation is a really, really important thing. A definition. A function from the plane into the real numbers is harmonic if it satisfies the Laplace equation. If u and v are harmonic and satisfy the Cauchy-Riemann equations, then they are called conjugate harmonic. So conjugate harmonic functions are somehow equivalent to complex analytic functions. That's really important, and we've explained exactly how this is, but it doesn't stop it from feeling any less magical. And this is an example of something which I think is much more impressive than Euler's formula. You can understand why people might have taken some time to figure this out, and why it hasn't entered popular culture. Because explaining these concepts is difficult. Explaining the relationship between these things is much more difficult than a simple equation. But mathematics is about connecting ideas. These are ideas. Conjugate harmonic functions is an idea. Complex analytic functions is an idea. That they should be connected in this way is interesting. It's wonderful. This is a much more important result than Euler's formula. Much more interesting, in my opinion. Now, the Cauchy-Riemann equations, let's say you have one u that is harmonic. The Cauchy-Riemann equations tell you how to get the conjugate function, because it satisfies partial differential equations. So you perform the various integrations. So if you have one harmonic function, you can build the conjugate harmonic function, and then you can build the complex analytic function. Yeah, see the notes for this. So u determines v. V determines u via the Cauchy-Riemann equations. There's lots of examples in the notes. I'm just going to do one. uxy equal to x squared minus y squared. Del u del x is 2x. Del u del y equals minus 2y. del u del x has to be equal to del v del y. So now we have del v del y equal to 2x, and that implies that v is equal to 2xy plus some function of h of x. We know that del u del y is equal to minus del v del x, so that implies that del v del x is equal to 2y, and that implies that v is equal to 2xy plus some function of y. And when you look at these things and squint a little bit, you realize that v has to equal 2xy. So now we have u equal to x squared minus y squared, and we have v equal to 2xy. What's the function f? F of z is equal to x squared minus y squared plus I 2yx, and that happens to be equal to z squared. Just check it, do the algebra. So, complex conjugate harmonic functions can be determined via the Cauchy-Riemann equations. Onwards, 3.5 theorem. Don't worry, we'll come back to all that stuff you've seen before. Those are ideas which are enduring. Suppose is a power series with radius of convergence R, then S is analytic on right everywhere that the power series converges, and S dash of Z is equal to the sum, and just what you'd expect, n a n z n minus 1, and S dash has radius of convergence R. Corollary. Proof, check out the notes, have a look at a book on complex analysis. So let's suppose our function has a power series in some open set, and the convergence all works and so on and so forth. Then within the radius of convergence, f of z is equal to f of 0 plus f dash of 0 z plus f double dash of 0 z squared, and so on. Proof, you do it. The notes provide a bit of a hint, but basically this just says that power series work exactly the way you'd expect, and that they are pretty much what you'd expect in comparison to the real numbers. They behave the way you'd think they should. Section 3.6. Theorem. If f is a complex number, is analytic on some neighborhood of z0, and f dash of z is equal to 0 for all z inside the neighborhood, then there exists some number c, so that f of z is equal to c for all z inside. Yep, pretty much what you'd expect. If the derivative is 0, then the function is constant. Let f from complex numbers to the complex numbers be given by f of z, f of x plus I y is equal to u x y plus I v x y. Be analytic on some neighborhood of z0 if any of the following are true, then f is constant. 1. Well, for all z inside my neighborhood, f dash of z equals 0. That follows from the result above. In fact, all of these follow from the result above and a little bit of tinkering. For all z inside the set, u x y 0, where z is equal to x plus iy. Because this, of course, implies by the Cauchy-Riemann equation something about v, which implies something about f, and we have the similar statement. I'll rewrite it like this. If the modulus of f of z is constant on the neighborhood, the other alternative is that the complex conjugate of f is analytic. Now remember, we've done some differentiation of complex conjugates, and complex conjugates don't behave very well with the derivatives. So if the complex conjugate is analytic, that implies something interesting, namely that the function is continuous. Alright, all of this is an example. The only, the only thing here that is worthwhile pointing out is that number 4, if the modulus is equal to 0, then done. If not, then u squared plus v squared equals r squared, and you can use this to derive information that the partial derivative with respect to x of u is equal to the partial derivative of v with respect to x, which equals 0, and you get back to similar results using Cauchy-Riemann equations. Why is it important to know when functions are continuous? Well, continuous functions are, I guess, very simple in some sense. It does crop up quite a lot when you're doing integration. It's a technical thing which can be useful. Also, it gives extra information that might provide you with some ideas about how these functions behave on the complex plane and analytic things in general. Okay, section 3.7, exp. And this gets back to something that I promised very early on. Definition. To find exp from the complex numbers into the complex numbers is defined as exp z equal to the sum n equals 0 to infinity zn over n factorial. 1 plus z squared over 2 plus z cubed over 3 factorial, and so on. Okay. Now we've shown previously that it's absolutely convergent, and we showed that in a previous lecture. So radius of convergence is infinity. In fact, it's entire because of that. And we showed it's entire. We know what the power series is, so we know what the derivative is. We can calculate it. d dz exp z is going to be equal to the sum n equals 0 to infinity n z n minus 1 over Now, 0, so it's actually, how do I put this? The first term, which is constant, will be 0. The other terms, after I reindex, and that's the definition that I used to motivate originally that exp I theta equals cos theta plus I sine theta. Motivation in chapter 1. Okay, and now real analysis implies that cos of theta is equal to sum minus 1 n over 2n theta to n, and that sine theta equals minus 1 n over 2n plus 1. These are Maclaurin series, so you should check them. Taylor series about theta equals 0. And you should check that. Prove that this implies that exp I theta equals cos theta plus I sine theta as claimed. So yeah, instead of actually proving everything properly, I'm just leaving it to you. But you can check that. It's a lot of algebra, really, is what it boils down to. But it's worth doing. You'll learn some things and get better at manipulating complex numbers. Proposition for all A and B inside C, exp A plus B is exp A exp B. Proof is interesting. So fix C inside complex numbers, then d by dz, ez ec minus z equals 0. So f of z equal to ez ec minus z is constant, and hence f of 0 equals f of a, which is equivalent to saying, well, it's 0. ec equals, and a is ec minus a. So if c equals a plus b, we get ea plus b equals eaeb, as required. Isn't that interesting? Constant functions, very useful. Lemma 1. For all z inside C, ez is not equal to 0, and 1 over ez equals e minus z. 2. If x is from 0 to infinity, then ex is real, and ex is greater than 1. If x all results you know, but prove them for a function that you haven't seen before. last thing, 6, is that EZ has periods given by 2k pi I. K is inside Z, which is not so surprising given the relationship to cos and sine. Right. Proof. Okay. Much of these are left to your own devices, and you should be done by yourself. There is full details inside the notes. So, in fact, I will let you work on those yourself. The notes provide some information about them and some hints. It's worth doing. Most of them, in fact, rely upon manipulations and various choices for A and B inside here, and in particular this does too. So, give that a go. Trig functions. Of course, we know values of trig functions on real values, and we defined them using a power series previously. Here I'm going to define them on complex numbers, and I'm going to do that via the exponential function. And this is the real part of EIZ, which should not be too surprising given what you've seen already. I'm sure you saw that coming. EIZ minus E minus IZ over 2 equals the imaginary part of EIZ. Okay, some examples. Cos of I equals E minus 1 plus E over 2 equal to 1, which is interesting. Since EIZ is entire, sine of Z and cos Z are entire. They're power series. What are those power series? They're exactly as you saw before. Cos Z equals the sum minus 1 n, except instead of using real values in here, we have complex values. Okay. And a list of properties for these functions. 1. Cos and sine have periods. 2k pi for all z inside the complex numbers. Cos squared z plus sine squared z equals 1. Proof. Exercises. For all a and b inside the complex numbers, cos a, cos b minus sine a, sine b equals cos a plus b, and cos a sine b plus sine a cos b equals sine a plus b. dz cos of z equals minus sine z, and dz sine z equals cos of z. And you can define other trig functions just as you normally would. So, for example, tan z is sine z over cos z. And similarly, for other trig functions. Boom. Page 11. Hyperbolic functions. I think I have to stop very soon. Definition. Cosh h of z is ez plus e minus z. Sinh of z equals ez plus minus e minus z over 2. So if you do the math, cosh z squared minus sine squared sinh equals 1. D dz cosh of z equals sinh of z, and d dz sinh of z equals cosh of z. Examples: sine I equals I sinh 1, cos I equals cosh y, and so on and so forth. The real part of cos x plus iy equals cos of x cosh of y, and the imaginary part of cos x plus iy is equal to sine x sinh y, etc. So what are the relationships here? Which things are harmonic? Which things are conjugate harmonic? It's an interesting question. You should try and work it out. And I'm going to actually stop there. I didn't quite manage to get there. So section 3.10 will have to remain undone. We will come back to it. Cheers.